Alright, today we are going to do something special, which is I try to videotape my lectures, okay? Then I probably will upload it to YouTube, so those who are not here can watch it. Because I also have an online class, obviously they will not be here at all, so I hope they can watch it a little bit. Okay, so how do you feel about your midterm exams? Okay, right, not too bad.
Some of the multiple choice threw me off a little bit.
Okay, so otherwise you are happy.
Yeah.
Good, good. So the last thing I want you guys to be is to be sad. Okay.
Good evening to you too.
All right. Good evening to you. Speaking of sad, let me ask you a question. What kind of professors are sad? Are always sad?
Is it one right in front?
Maybe, yes. But it's actually, I mean, by the way, do you guys love archaeology? So archaeology professors are always sad because their jobs are always in ruins. Okay, so today's topic is linear programming. Okay,
Is that why you're sad?
that's why I'm happy today. So today we're going to go through a few topics. So basically, those are the basics of linear programming. So let's have an overview of this course. So this course is about models, right? We use models to help us make decisions, hopefully make better decisions, okay? So in the first half of the course, we talk about decision analysis, Monte Carlo simulation, QE models, and arena dynamic simulation. Okay? So those models focus on stochastic stuff. Okay? So lots of things are random. But starting from today, from the topic of linear programming, we are going to talk about deterministic models. That means most of the parameters in the models are assumed to be constant, to be given, all right? So linear programming first, then we're going to talk about something very related, integer programming. So some of the, try to refresh your memory, some of the components of mathematical models, right? Decision variables, on what you make a decision. And objective function, so what's your goal? Is it maximize profit or minimize cost or maximize revenue? So many things. Of course, there are lots of constraints, right? So constraints can be in terms of resources. You don't have this much money, right? Or you only have, say, 20 people available. Sometimes, it's policies like unions, they always have some policies about how you can schedule workforce, right? And then parameters. So those are the basic components of models, right? So what is linear programming? So linear programming, first of all, is too long, so I'm going to call it LP all the time. So LP is a technique, okay, which is to optimize a linear objective function subject to linear constraints. So constraints can be equalities or inequalities, okay? And of course, when we say linear programming, obviously there might be something called non-linear programming, right? So non-linear programming probably is more realistic because in real life most of the things are non-linear, but linear programming is is a first step to learn stuff, right? And of course, you can also approximate lots of things in real life using linear equations. Okay? So we can model lots of real-world problems, okay, as LP models or LP problems. So we're going to see those problems as we move along. Okay? So how do we formulate LP model? How do we formulate a business problem into an LP problem, right? And of course, those are the 3 steps, very, very general, okay? So I don't think you can learn anything from those 3 steps. But one thing we can see is that, units is quite important, okay? But just like in the, in the waiting line models, sometimes you use per minute, sometimes you use per hour, and so on. You have to be consistent. Okay, so we're going to start with very simple examples. Okay, so one of the simplest examples are 2 decision variable problems. So where you make only 2 decisions. So because it's 2 decisions, right? So you can kind of draw a picture and show it graphically. All right. Of course, in real life, you might have to make 3 decisions, 4, 5, maybe 100, right? So here's a very simple, or might not be that simple question to start with. Okay. So we have 6 large blocks and 8 small blocks. Okay. And we can make 2 kinds of products, chairs or tables. If you make a chair, you need 1 large block and 2 small blocks. If you make a table, you need 2 large blocks and 2 small blocks. Okay? And then you have the profit. You make a chair, you can make $10. You make a table, you can make $16. The question is, what is the best number of tables and chairs to make? So how about you guys take a few minutes to solve this problem. The goal is to maximize profit, and you can ignore this constraint for now. Just use this slide and figure out what is the optimal number of tables and chairs to maximize profit. Okay? I give you like 2 minutes, please. Okay, so what did you get? Yes.
4 chairs and a
How many chairs?
table.
4. How many tables?
1.
1. Hmm. That might not be possible.
No.
Yes.
2 chairs and 2 tables.
Okay, so how did you get that?
Well, I used the numbers.
Use the numbers. Did you kind of try all the combinations?
Yeah, I tried to use all the resources possible
Okay.
and figure out what's the maximum profit.
Yeah, yeah. What did you get?
I said if you just use up, if you take 3 tables,
Yeah,
and then you don't have enough left for shares, but
that's
give
right.
yourself 64, the profit.
64.
Oh, sorry, no. Sorry, 96.
I think it's 48, right?
Yeah.
If you make 3 tables, right? Did you say 3 tables or 4 tables?
No, sorry, it's not drawing, sorry.
Okay, so this problem, looks simple enough, right? But you do try and error. It's not really that obvious. But what you can try is, if you just make chairs, right? If you just make chairs, you can think, what's the maximum number of chairs you can make? Let's go with the tables first. What's the largest number of tables you can make? That would be 3, right? We can only make 3 tables. You can make 3 tables, which needs 6 small blocks, make 48 profits. But you have 2 small blocks unused, right? So that's like an extreme case. On the other extreme, you can make only chairs, right? What's the maximum number of chairs you can make? So if you check the numbers, chairs you can make 4, right? So the maximum is 4. And you need 4L and 8 small blocks to make $40 profit, right? But you have 2 large blocks unused. Obviously, if you have something unused, you might want to say, maybe I can do better, right? So, okay, and because tables has a higher profit margin, right? So you probably want to try to make as many tables as possible, right? So you make 3. You have 2 small blocks left, okay? So how about you make just 2 tables? So you want to think what's the mix of tables and chairs you can make to maximize profit, right? So 3 tables is the maximum, right? But then you have something left unused. How about you go down, you just make 2 tables, right? If you make 2 tables, you're going to need 4 large and 4 small, right? And then you have 2 large and 4 small left, right? That would be 2 chairs, okay? That would be 2 chairs. So if you do that, you can verify this easily. You can make 2 tables and 2 chairs. And nothing is left, okay? That might be a good sign. Then you can calculate the profit, right? So the profit is 2 tables, so 2 times 16 plus 2 times 10, which is 52. So this is like a trial and error, right? You just try it, and of course this example is simple enough, right? But suppose you have hundreds of large blocks hundreds of small blocks and you have, say, 10 products to make, right? Then you cannot just list all the possibilities and try to be lucky, right? It's not going to work. So now let's formulate this problem as an LP problem. So LP means linear programming problem, and we try to solve it, okay? So the first step is to define the decision variables. So in this example, obviously, you have two decisions to make, number of chairs and the number of tables, right? And then you want to specify your objective. For this case, again, it's simple enough. We want to maximize profit, right? And obviously, that's how we write out the profit function, right? And the next step is to kind of identify all the constraints, right? In terms of resources, in terms of maybe some other kind of resources, right? Other kind of constraints. So it's not difficult again. So because you only have 6 large blocks, right? So if you produce x1 chairs, then you need 1 times x1 large blocks, right? If you make x2 number of tables, okay, then you need 2 times x2 large blocks, okay? So this is a requirement from the chair. This is the requirement from the table. What you need cannot be more than what you have, right? So that's a constraint. Similarly, you have a constraint for small blocks. And as we saw in the previous slide, we have a constraint which says no more than 5 tables. I mean, we write it out. That's how we do, right? X2 is less than or equal to 5. And sometimes we also have some implicit constraints, right? It doesn't say specifically, but it's common sense. X1, X2 has to be non-negative, right? But it is possible that X1 is 0, right? If the profit margin of chairs is very, very low, then you probably make X1 equals 0. Yes.
Wouldn't this be not more than 3 tables? Because you can't make 5 tables regardless.
Yes, you are right, and excellent. But here, let's assume someone, your boss, which is not as smart as you, give you this constraint. Okay? So this is an implicit constraint, non-negative. Any other constraint you might think of? Yes.
You can't have half a table or half a chair.
That's right. So another implicit constraint is x1, x2 have to be integers, right? So this is a good point, but it's a little bit tricky. First of all, many LP problems, you can solve them by ignoring these constraints. Okay? At least at first, you can ignore these constraints. If you insist on using those constraints from the very beginning, maybe the solution is not very easy. Okay, you have to solve lots of things to find the answer. Okay, so for many other reasons, let's assume we can ignore these constraints for now. Okay, the next topic we are going to talk about is called integer programming. That is, how can we force all variables, not all variables, but some of the variables to be integers. Okay, but for now, let's ignore these constraints. All right. For now. All right, then we have LP problem. We have an LP model. We got everything here, right? So just a reminder that don't forget about this one. We all, somehow we want to make sure you understand. this constraint is there. If you don't use this constraint, your solution might be very funny. Okay. So how can we solve this LP problem? Okay. So linear programming problems, we call it LPP, just to be simple. As we said, you can always use trial and error, right? And next we are going to talk about how to solve them using graphical methods. So using pictures to solve it, right? So when you draw a picture, probably it's easiest to draw two-dimensional pictures, right? You know, 3-dimension is difficult. 4-dimension is probably impossible. Okay, so let's talk about problems with only 2 decision variables. Okay, and of course, when you use a picture, you can visualize things, and hopefully that help us understand the logic behind LP techniques. Okay, so we're going to use those terms throughout the LP, lecture. So like feasible solution, infeasible solution, and so on. We're going to see them one by one. Okay, so to use graphical methods, we want to follow a few steps. Okay, so there are 2 versions of the graphical methods. The first one is called objective function method. Okay, next one we're going to talk about, I think it's a corner point method. Let's do this one first. All right. So there are 3 steps. The first step is to identify the feasible region. The second step is to try to generate an arbitrary objective function line. And the third step is to move the objective function line either towards the origin or away from the origin and see where the objective function can be maximized. Okay, so again, those steps are listed here for your information, but we're going to, of course, look at them one by one. So how do we identify the feasible region? For example, we have constraints, right? Constraints means something you have to satisfy, right? So for example, x1 plus 2x2 is less than or equal to 6. Okay, that's a constraint. What does this constraint look like on a picture, right? Well, something you probably know already. First of all, you try to plot the boundary line, right? What is the boundary? And you want to see, once you have the boundary, you want to see which side you are in, which side you should be in, right? So there are 2 types of constraints, okay? So this type of constraint are inequality constraints because less than or equal to, right? This means an area, okay? Sometimes you may have some equation constraint. For example, you must have x1 equals 2x2. For example, sometimes you say that the number of chairs must be twice the number of tables. In that case, x1 equals 2x2. That is equality constraint, right? But this is more often, right? Okay, so if you go back to the LP, right? So let's go back here. This model, let's say we have 4 constraints, right? 1, 2, 3, 4. Maybe this is 2 of them, but we just say 1 of them, right? So let's do this one first, which is the easiest. So x1 non-negative, x2 non-negative. So basically we have this plane, right? Now, how about the constraint at the top, x1 plus 2x2 less than or equal to 6? What is the region? Well, as we said, first you draw the boundary line, right? Boundary line means equal, right? And then you can find 2 points. Then you can draw a line. Okay, so the easiest way is to see what are the intercepts on the x1 axis and x2 axis, right? So, again, that's how you find the x1 intercepts and x2 intercepts, right? Then you have this line, okay? And then you want to see which side you should be in, right? You have 2 sides. Again, this might be trivial to many of you guys. Sometimes it's not trivial to others. Okay. The easiest way is to find the point. Just select any point, like the origin. Okay. 0, 0, right? 0, 0 is less than 6. So this is feasible. This is in the constraint. This satisfies the constraint. That's why we are on this side, right? We are on this side, okay? Another constraint, right? We say, is it? Oh, that's the same one, okay? But the next constraint is 2x1 plus 2x2 less than equal to 8, okay? We have the same thing, right? You draw a line. You make this equality, right? Then you draw a line, then you see which side is it, okay? So you can see, you can check, this will be the line, this will be the boundary, okay, of that constraint, and is the downside or the upside, okay? Again, you can use 0 as a test point. 0, 0 is less than 8, of course, also in this side, right? So this side. So you have this constraint line, this boundary, and this side. You have this boundary and that side. Okay. The overlap would be the region where the 2 constraints satisfied at the same time. Right. So this is the region where the 2 constraints are met, are satisfied at the same time. Of course, we don't want to forget this one and that one, right? x1, x2 are non-negative. And remember, we also have another funny constraint, which says x2 is less than or equal to 5, okay? And, if that's the way you draw the picture, this is the x1 axis, and it's x2 axis, then of course this is x2 equals 5. Less than 5 means going down, right? But as you can tell, this constraint is kind of funny because it's redundant. It's redundant, right? Because you have identified this region already, and for this region, that constraint will be satisfied automatically. Okay, so that constraint is redundant. Well, sometimes it happens. Okay, sometimes you may have some redundant constraints. So if you want to say it's a constraint whose existence doesn't matter at all. Okay. So this is a picture, right? We want to find out what is optimal combination of x1 and x2, right? So graphically speaking, every point within this area is feasible because every point in this region, satisfies all the constraints at the same time. Okay. So we call them feasible solutions. Feasible solutions. So if you don't violate any constraint, it is feasible. If you violate if you violate at least one constraint, you will be infeasible. Okay. For example, this point satisfies this constraint, right? But not that one. Not that one. Okay. So this is infeasible. This is infeasible. This is feasible. Okay. And we also call those corner points. which makes sense because those are the corners of this feasible region. Okay, corner points. So of course, those corner points, they are corners, so they are the intersection of two lines, two constraints, two boundary lines. Okay, it may happen that certain point may have three lines intersect together. It's possible, not very likely, but it's possible. But most of the time, it's the intersection of two lines, two boundary lines. Okay, correspond to two constraints. So in this example, we have 4 corner points. To be more precise, we have 4 feasible corner points. So you can also call this corner point, but it's infeasible. Okay? So we have complete the first step. Okay? So I just see an interesting cartoon this afternoon, which says, I hope you guys like linear programming because I want to be in your feasible region. I don't know what that means exactly, but it sounds funny to me. Okay, the second step is to figure out what the objective function looks like. Okay, so the objective function is z equals 10x1 plus 16x2, right? So this is a line, but it's not a definite line because you don't know what z is, right? So you can just assign an arbitrary value to z first and see what is the line. Because, for different z values, the lines will be similar. You just have to move it in parallel, right? So it doesn't matter too much probably. So for example, let's say we want to use z equals 20 first. Okay? So then we have this line, right? 10x1 plus 16x2 equals 20, right? And then let's draw a line. How do we do that? The same thing, you just figure out probably the intercepts, right? And then you draw the line. And you can figure out the 2 points, 2 intercepts, and then you can draw the line. So that is the objective function line. Okay, that is the objective function line. Now, this objective function line kind of crosses the feasible region, right? So every point on this line is feasible, first of all. Second of all, it's going to give you a z value of 20, right? Now, you want to maximize z, right? Of course, when we say maximize, we mean we want to move up. We want to move up, right? And when we move, we have to make sure the slope will be the same, right? Will be the same, like move in parallel, okay? So let's say, how about we make, okay, nice animation here. Now we can check if z can be 30, okay? So you make z equals 30, and then you have a line, again, it's 10x1 plus 16x2 equals 30, right? Let's draw the line. It will be here, okay? Used to be 20 here, now it's 30 over here, right? Of course, you can still do better. You can still do better. So what is the best? What is the best? Okay? And we know that if this line moves further away from origin, it's going to be better, right? Of course, if you go here, if you come here, this point, this smiley face, this point when your objective function line touches this point, okay, then you cannot move further, because if you move further, this line will be out of the feasible region, right? So this point is the point which you will maximize Z, the objective. Okay? Does it make sense? So graphically speaking, we just move the objective function line away from the origin until it hits the last feasible point. It might be more than one, but you want to make sure it cannot move even further. Okay, so that is one method, and of course we know this point is 2, 2. This point is 2, 2. How do we know that? Because if you solve this boundary line, this corresponds to an equation, this corresponds to an equation, right? You solve those two equations simultaneously, you will find out this point is 2, 2. So this is the optimal point. Then what is the optimal Z? Well, just use 2, 2 in the objective function. You find the Z is 52. So that is optimal. That is the maximal value you can achieve. All right. So the second graphical method is similar but slightly different. It's called corner point method. So this method uses a property of LP problems. Okay, so somebody has proved that somebody has proven that this is true. So it says that the optimal is always achieved in corner points, okay, or in the optimal solutions. Maybe many, maybe just one, but at least one of optimal solution will be a corner point. So this tells us, let's just try to identify all the corner points, right, and see which one gives us the maximum objective function. Okay. So in terms of the steps 1, 2, 3. The first step, again, is to identify the feasible region. The second step is to identify the feasible corner points. So once you have identified the feasible region, then it's easy to identify the feasible corner points, right? And third step is to plug the corner points into the objective function formula and see which one is the best. So again, this is the LP, and we have 4 corner points, and A, B, C, D. No, A, B, C, D. Okay. So we have the coordinates. So remember, this is corner point 2, right? So what you do next is just plug those numbers, those coordinates into the objective function to find out which one is the best. So no surprise here, this is the best. Okay. Okay, so I guess this method depends on depends on if you can find those coordinates, right? So how do you find the coordinates? How do you solve, like 2 equations simultaneously? Okay. Well, I'm pretty sure I want to skip this because I don't want to insult your intelligence. Okay. So how do you solve 2 linear equations simultaneously? But if you really want to check, you can go ahead. Okay, so now we know how to solve a LP problem graphically, right? And sometimes it's important to identify what kind of constraints we have. Okay, so we can say that there are 3 types of constraints: redundant constraint, non-binding constraint, and a binding constraint. Okay, so let's check those one by one. So redundant, as we said, that means whether it exists, or not does not matter. Okay, like this one, right? This is a redundant constraint. So it's not, does not affect the feasible region. It's not part of the optimal solution. And then we have something called binding constraints. Binding constraints. So binding means what? First of all, we have the feasible region, right? And this feasible region, is in this feasible region, you can see there are 4 boundaries, right? So 1, 2, 3, 4, okay? And two boundaries are, this is the optimal point, right? Optimal solution. So this optimal solution is intersection of 2 boundaries, okay? So in other words, this optimal solution is given by 2 constraints, okay? So those 2 constraints, they are part of the feasible region, okay? They are also part of the optimal solution, because the optimal solution lies on those 2 boundary lines, okay? So we call those 2 binding constraints. It is binding because at optimal solution, those inequalities will become equalities. Okay? At optimal solution, right? This 2x1 plus 2x2 will be 8 exactly. x1 plus 2x2 will be 6 exactly. Okay? And then we have the non-binding constraint. So non-binding constraint, because they form the feasible region. So this boundary and this boundary, they contribute to the feasible region, right? But those 2 boundaries are not part of the optimal solution. In other words, the optimal solution is not on this constraint and that constraint. Yes?
With the graphical method, does it matter which method we use? Like in an exam, are you going to be like use the corner point method? Or
We need to use both. We need to know both. Yes.
But what about her question? Is do you care which we use?
I may tell you so. Yes. Because that makes me happy. So we want to know both because we want to understand the logic behind the LP techniques. Okay. Okay, so we got like a relatively simple example, right? Now let's look at something, more or less real. Okay, how about you guys take 1 minute to check out the problem? Okay, so a company is making two kinds of products, a regular glove and a catcher's mitt, right? Then you have a few constraints in terms of the production time, production hours in different departments, right? Then you also have something like a policy-wise, okay? For example, we want at least 200 more regular gloves than catcher's mitt, right? So that's not really a resource constraint, it's more like a policy for whatever reason, right? And different product is going to consume different times, right, in different departments. So here's a table, right? We also have a profit margin of each product. Obviously, we want to maximize profit, right? And the decisions to make are the number of regular gloves and the number of catcher's mitts, okay? So we have this maximization problem. This is the objective function. Then we have a bunch of constraints, okay? For example, so in the cutting department, let's just call it the cutting department, okay? It has 900 hours. So this department has 900 hours. So the number of hours you can use will be 900 or less, right? So if you make, if you want to make R, regular gloves, C, number of catcher's mitts, right? Then you need R plus 2C in this department, okay? So R plus 2C has to be less than what is available, right? So that's why we have this constraint, okay? We can call it cutting constraint. And similarly, you can have constraints for the finishing department and the packing department, okay? Then you have something else. For example, you want to make at least 300 gloves in total, right? So that means R plus C is 300 or more, and so on, okay? Again, as we said, theoretically speaking, you probably want to limit those variables to be integers, but most of the time, so many times, you can ignore them first, okay? Now we want to use the graphical method, okay? For this problem, you probably cannot use trial and error method, right? Because you have too many constraints there. But you can draw a picture, okay? So we have 6 constraints. 6 constraints, so you have 6 lines, okay? So you list all the lines there. You will find out this yellow region will be the feasible region, okay? And this feasible region is formed by this constraint, and this constraint is what? That is, I believe this constraint, okay? This constraint, that's the finishing constraint. And this constraint is R minus C larger than or equal to 200, okay? And for example, this constraint is the packing constraint, okay? It's the packing, which is 0.125 R plus 0.25 C. So as you can imagine, right, it's probably not too easy to draw those lines, right? But if we use the graphical method, that's the way to go. Okay. Once you have the feasible region, then you have to have objective function line, right? So what's the objective function? That is Z equals 5R plus 12C. So by the way, okay, again, for some of you guys, probably not too many, to draw the boundary lines sometimes not that easy or sometimes can be a little bit tricky. Okay, for example, this line is r minus c larger than or equal to 200. Okay, and this is the feasible side. Why? Well, it's not too complicated, but you have to pay attention that this is the r axis, okay, and this is the c axis. Okay, so for me, usually it makes sense to rewrite the constraint, right? So if I want to write it, probably c less than or equal to r minus 200, because I make the c the y-axis. Okay. So then you can do the same thing. If r equals 200, c equals 0. So 200, 0 is a point. So 200, 0 is a point, right? And that line has a slope of 1. So looks like this, right? Looks like this. Okay, now for that particular objective function line, again, we said that we want to draw the line. So we move the line, away from the origin and see which is last point is going to touch, right? Which last point is going to touch. Now, how do we know which point is last point to touch? That depends on what? That really depends on the slope of the objective function, right? For example, if this is the objective function line, and this objective function line is pretty steep, right? And then, what is the last point it's going to touch? Again, as it moves away from the origin, the objective function is going to be larger and larger, right? So I'm pretty sure this is last point. This is last point it's going to touch. So this can be optimal if the objective function is very steep. My son, eh? Now, on the other hand, if it's very flat, then if you move away from 0, I'm pretty sure this last point you will touch. Okay? So it really depends on the slope. Okay? So you really have to know what is the slope of the objective function. To be more precise, you have to know, is this objective function steeper than this line or not? Okay? Is it steeper than this line? As we said, if the objective function is steeper than this line, then that's going to be the optimal, right? If the objective function is flatter than this line, then this is going to be optimal, right? So the key is to compare the slope of this line and the slope of the objective function, okay? And this constraint, this boundary line is the packing one, okay? So what's the slope of this packing constraint of this the boundary line of the packing constraint? Okay, so let me just write here, okay? Slope equals, so can you tell me what's the slope of this objective function? Sorry, of this constraint, of this boundary? What do you think, Captain? The packing constraint. One half, and that's correct, or almost. It's negative one half, right? So that is the packing constraint line. And what is the slope of this objective function line? it is
Sorry, which one?
the objective function line.
What's that?
Over there. Say that again.
I mean, which line is it?
Over there.
Yes, that's a name. That's slow. That's a word.
That's the objective function line.
Ah.
Yeah, you make set whatever value you like.
Oh, well, I'm not really paying attention too much, so I don't know.
That's very inspiring. Thank you.
I do what I can.
Can I count on you
Sorry, no.
or your friend? Phone a friend. You? Not this time? Okay. So what's the scope of this objective function line? You know, we know this one, we probably know this one as well, right? But you guys probably don't want to tell me the big secret. So I'm going to tell you, it is minus 5 out of 12. Right? Now, slope here, slope there, which one is steeper? When I say steeper, I mean something like this, right? This is flatter, this is steeper. Correct. Okay, so this line is steeper, right? In other words, the objective function line is flatter. So that's why the objective function line is something like this. Not that, but this. Not that, but this. Got it? This, right? So it's flatter. So that's why if you move the line, this will be the last point you're going to touch. Okay? This is the last point you're going to touch. So that's why this is the optimal point. This is the optimal point. Okay, so that is the graphic method number 1, the objective function method, right? And the second method is the corner point method, which probably is simple. You just have 4 corner points, right? How about you just check, you know, the optimal, you check the objective function value at each and every point and see which one is the highest, okay? So again, I probably don't want to insult your intelligence. So this is the objective function, right? Just plug in the numbers. So this is 400 times 5 plus 200 times 12 equals 4,400, okay? And this is 4,000. And this is the winner. This is the winner.
So why would you ever graph it if you could just do that?
Because we can.
That doesn't mean you should.
You know, we try to impress someone, right? That's
By graphing things?
could be, yes. But if you think about it, right, this method may not be feasible. I mean, again, that depends on if you have like hundreds of corner points. Okay. Maybe it doesn't apply here, but anyway, this method is not, you know, not much fun. This is fun, so we want to do that. Okay. So I want you guys to know both because at the end of the day, this is the basic logic when you do the linear programming stuff. Okay, so now we want to have more fun, which is to identify what kind of constraints they are. Is it binding, non-binding, redundant? Okay. So as we said, binding constraint is very simple. Just first you find out where is the optimal solution. So this is the optimal solution, right? Every boundaries cross this optimal solution will be binding, will correspond to binding constraint. So this corresponds, this is a binding constraint, this is a binding constraint, okay? You just have to make sure you remember what this is, what that is, right? Now, this yellow region, the physical region, right, is formed by 4 lines. So these 2 lines these two lines, they are part of the feasible region, but not part of the optimal solution. So those two lines correspond to non-binding constraints. Okay. So we also have some redundant constraint. Okay. So this is redundant because its existence doesn't matter. Okay. This is redundant constraint. So I guess we just covered those things. We have two redundant constraints. We have sometimes we kind of classify redundant constraints as one kind of non-binding constraints. Okay. Sometimes we do that too. So again, if we want to use a table, right, and we can do the binding, non-binding stuff. Okay. So we have the constraints. And we have optimal solutions, right? 400, 200. Objective function value is 4400, right? And given those optimal values, we can find out what is left-hand side. Okay. Then we compare those left-hand side of those, inequalities with the right-hand side. Okay. So for example, R plus 2C at this point equals 800. Okay. So at on the left hand side is 800, on the right hand side is 900. Okay. So which is not binding, right? When we say binding, we mean they are equal. They are equal. So we can figure out the rest. For example, this constraint, right? On the left-hand side is 100. We got 100 by plugging those two numbers into the left-hand side, which is 100. The right-hand side is 100. So left-hand side equals right-hand side, so it is a binding constraint. Okay? You can figure out the rest. So no, not binding, yes, it is binding. Okay, so one of them is actually redundant, right? But sometimes we just classify redundant constraint as non-binding constraints. Okay, so let's not worry about the slack and the surplus for now. Okay, but
Can we do that on the test? Can we just cross things off on the test?
Oh, we can talk about that later. Yes. So much fun, we cannot just drop that, right? So graphical methods, yes.
So just stepping back a bit, how come in the second example we graph the objective function, but in the first example we only graph the constraints?
The first example you mean
With
here?
2 lines, yeah.
Yeah. Well, we do have the. Just have to go way back. Remember those things? Yeah. So this is the objective function line.
Okay.
This is if you move the objective function line away from the origin, right? Yeah. We do have the objective function lines here.
Okay.
Yes. Okay. So of course, graphical methods are not really practical. Okay, but we can use those to see what's the fundamental ideas of LP. So a more realistic technique is called simplex method. Okay, so simplex method, and of course you can do simplex method by hand for smaller problems, but for larger problems we have to use computer solvers. So as you will see later, Excel solver is our focus. Okay, how do we solve LP problems using Excel solvers? Because simplex algorithms, methods is quite important, so we just want to mention them really quick. Okay. So in LP problems, people have proven that if LPP has an optimal solution, at least one corner is optimal. In other words, at least one optimal solutions will be one corner points. Okay, so that's why we want to start with corner points. So simplex method has a very efficient algorithm to find the optimal solutions without checking all the corner points. Okay, because sometimes you just have too many corner points. But we don't have to know how simplex method works exactly, which is not required, and it's actually not required for any business courses. Okay, so but in simplex method, we are going to use the standard form of LPPs, linear programming problems. So what do you mean by standard form of LP problem? If a LPP is standard, then all the constraints are equalities. Okay? All the constraints are equalities. So if you don't have equalities yet, it's very simple. You can add in slack variables to this kind of constraint. This kind of constraints less than or equal to. You can add. You can subtract surplus variables from this kind of constraints. Okay. Okay, so let's check really quick. Not that they are super important. Okay, slack variables relate to this kind of constraint, like this. Okay, because less than or equal to 5, so there might be some kind of slack. Okay, so if you say I define a slack variable which is s1, then you can have an equal sign, right? You can find the value of s1 such that this is true, right? On the other hand, you may have some surplus constraint like this. I'm sorry, not surplus constraint, but this kind of constraint. Okay, larger than or equal to, like this. Okay. So the left has to be at least 10. Okay, so it can be 12, can be 13, right? If it's 12, then you have basically 2 of surplus, right? So if you want to convert this into equalities, it's very simple. You just subtract the surplus variable, right? The surplus variable, then you can make it equal sign. And of course, when you define this way, then the slack and the surplus variables are non-negative. Okay, so in LP problems, we basically want all the decision variables to be non-negative. Okay. Again, this is another example. Okay, so we talk about the maximization problem, right? Now let's talk about the minimization problem, okay? So how about you guys take 1 minute to check it out? Then we can go through this together. Okay, so I guess for this problem, you're like a farmer, right? You want to use fertilizers and see, how can I, make sure I can grow my crops while minimize my, cost of fertilizers, right? So there are two types of fertilizers, and your field requires at least 16 pounds of this and 24 pounds of that, okay? And then if you buy one bag of super grow, that's how much you get, okay? If you buy the crop quick, that's how much you will get. And then you have the requirement of the field, right? So the requirements are here, right? 16 and 24. So how much of each brand to purchase to minimize the cost? So this is the minimization problem, and the decision variables are very simple. It's just the number of bags of super grow and the number of bags for crop quick, okay? And again, we just do the 3 steps, right? You want to define the decision variables, construct the objective functions, and identify all the constraints. So x1, x2, in terms of bags, okay? So bags of fertilizers, and the objective function is to minimize the cost, okay? Very simple. And the constraints are, you need at least 16 pounds of this and 24 pounds of that, okay? And if you buy one bag of, super grow, that's how much nitrogen you will get, right? If you buy X2 bags of, crop quick, that's how much nitrogen you will get, okay? So the total should be more than what you need, right? And the non-negativity constraint, and I'm not sure if you want to apply. If you want to apply the individual constraints, let's assume that constraint is not needed, okay? So graphical method, you just have to draw the pictures, right? So this is the two constraint lines, right? One is this one, the other one is that, okay? And of course, you need to know that we're talking about the upper side, not here, right? Because the sign is larger than equal to, right? So if you do the two constraints combined, actually including the non-negativity constraints, right? Then basically this is the feasible region. This is the feasible region. And next you can kind of try to find out what the objective function looks like. So this is the objective function, right? You assume this is 36, and see what it looks like, right? And it looks like this. Okay, this objective function line. So on this objective function line, every point is feasible. Not every point, but the point, this line segment is feasible, right? And on this line segment, the cost is 36. But you want to minimize cost, you want to ask yourself, can I move the line closer to the origin such that the cost can be minimized, okay, further? So you have to keep moving until you touch the last point. But as you know, which point is the last point? It really depends on your slope, right? So if this slope is very steep, right, and move closer to the origin, that will be the last point, right? If my objective function is very flat, if I keep moving, this will be the last point, right? If it's in the middle, then this will be the last point, okay? So you really have to check the slopes, right? So this boundary has a slope of, so can anyone tell me? Also this one. We have to go back a little bit, right? Let's come back here. So what's the slope of this function? Kyle?
It's negative either 2 or 0.5. I haven't decided yet.
Okay.
One of those good.
Yes. So it's minus 0.5.
Close enough.
Mhm. And then you have this constraint line. The slope is, I believe that is the constraint, right? The slope should be what?
Negative 8 over 6.
That's right. So, why not 4 over 3?
Because my way makes more sense because it lines up with the numbers.
Okay, so you have two constraints. They have different slopes, right? So what is the, so let me just come back here. So this is that. This is 1 plus 5. And then you have the objective function. The slope is what? Did I make a mistake? No. I never make mistakes, right? So this is minus 2. So it looks like this objective function is steeper than both lines, right? So relatively speaking, looks like this, right? So you have to move, and that is the last one you will touch. Okay, so this is the optimal. This is the optimal. Okay, so probably it's not that easy to draw those lines in a very precise fashion, but you just have to figure out the relative, steepness, right? So any questions? So if you want to identify the constraint types, of course, binding, non-binding, right? So, make sense? Okay, so, I mean, you can also, this one, can you use the corner point method? I think you can, yes, but it's a little bit tricky because, so make sure you understand this is not a corner point. This is not a corner point. You just don't want to draw to the infinity, right, and beyond. Okay, so we talk about LPP, one maximization problem and one minimization problem, right? And now let's talk about something crazy, okay? Irregular types of LPPs. So first is that sometimes when you formulate LPP, that problem can be infeasible, okay? So this is the example. So you want to maximize this, you have those constraints, right? So first, this 4x1 plus 2x2 less than 8, that is constraint. Okay? So here is the, so this corresponds to the first constraint, right? But then you can tell that x2 cannot be larger than 6, right? So at least this constraint and that constraint, they conflict with each other. So you don't have any point which can satisfy all the constraints. So the whole problem is infeasible. Okay? So can this happen? Can the infeasible kind of problem happen? I'm not so sure. It's more likely that maybe something when you do the formulation of the problem, maybe you have made some mistakes. Okay. Okay. Next one is called unbounded problem. Unbounded. Okay. So you have three constraints, basically two constraints, right? X1 larger than 4. X2 less than 2. So this shaded region is the feasible region. Okay. Now you want to maximize the function, right? And the slope is this. You want to maximize, so you want to move away from 0 as much as you can, which means you can go to your home, right? All the way. So it's going to be unbounded. Okay. Again, this very likely you may have made some mistakes. Okay. Maybe you forgot some kind of constraints. Now, if I want to say, if I want to ask you a question, what if you want to minimize instead of maximize this one? So if you want to minimize this objective function, which point is the optimal? Do you have optimal? Yes.
Maybe it's 0, 4.
This one, right? Okay, so I'm going to tell you very proudly, this is actually 4, 0.
Oh, sorry for that.
Just kidding. So if we change it to minimization problem, we do have an optimal solution, which is right here. Okay. Okay. Now this is quite likely to happen. I mean, sometimes it can happen. Nothing is wrong with it. Okay. So this objective function is 40x1 plus 30x2. Okay. And then you have basically two constraints, right? So the first constraint is 40, 20, so that is the line. That is the line, which one? Here, okay? So this corresponds to the first constraint, right? And then you have this constraint. Okay. I'm a little bit confused. X1 plus 2x2 less than 40. So it's 40, 20, right? So 40, 20, so that is that one. Okay. Okay, I'm going to use my magic pen. So 40, 20, so actually that is the, yes. And then you have the second constraint, right? And in terms of intercept is 30 and 40. So that's 30 and 40, so that is the, so this corresponds to okay, so here is the feasible region. Okay, now you draw the objective function, right, which is which has a slope of minus 4 over 3, okay, which is the same as this one. Okay, so if you think about it, the slope here and the slope there. Okay, so slope is minus 4 out of 3. This is minus 4 out of 3. So it happens the objective function and one constraint have the same slopes, right? Now, this is something like this, right? So you can move away from 0. So the last point, actually the last line segment you're going to touch is the whole thing here, okay? So this whole BC segment will be the last thing the objective function is going to touch. So everything, every point on this line will be optimal. Okay? So you have multiple optimal solutions, right? Of course, we are talking about something continuous, right? X1 is larger than 0, x2 larger than 0. So on this line segment, you have infinite number of optimal points, right? So you have multiple optimal solutions. Actually, you have infinite optimal solutions, right? Okay, so now I want to just summarize, make that very specifically, kind of state that very specifically that what are the characteristics, what are the properties of linear programming problems, okay? First, we need the proportionality assumption. Okay? That means everything is linear, right? So this is linear, this is not. So in an LP problem, this cannot happen. It shouldn't happen. Okay? So the second assumption is additive. So everything is additive or minus, right? You cannot have multiply. You cannot have two decision variables multiply or two decision variables, do the division stuff, right? So you cannot have something like this. And you also have something called divisibility assumption. That means everything is continuous. You also have the certainty assumption. That means the parameters are assumed to be constant. Okay. Okay, so some more like characteristics of linear programming problems. Everything has to be linear. Okay, the constraints can be less than equal to, can be equal, can be larger than equal to. And non-activity, right? You want to maximize or minimize a single objective. So this is something we just mentioned, right? Sometimes you may have multiple optimal solutions. Okay? So if you find two corner points giving you the same optimal solution, the same maximal or minimal objective function value, that means the line segment between like A and B, the whole line segment will be optimal. You have multiple optimal solutions. You have infinite number of optimal solutions. Okay? So does it make sense? So some of the properties of RPP, and this just for your information. Okay. So next we are going to solve. I want you guys to try two example problems, okay? So this is the first one, and this is the second one. And for those of you guys who are online, they are on the last few slides on your lecture notes, okay? So, okay. I guess, how about you guys take like I don't know, 20 minutes to solve those two, then you are ready to go home? Yes?
For the assignment, if we hand it in, and let's say like we change something and hand it in again, would it overwrite the previous file?
Yes. Yes. Okay, so you guys work on those two examples, and let the real fun begin. Okay, I think we can stop the video. Yes. So thank you. Bye.